metals. Acha, now, before I go for purification of metals, I like to tell something. Let me wrap it. See, when I have discussed you that first of all, what we do, we identify the ore, then ores are being collected, they are being purified by a very crude physical methods of purification is a very crude one because still the metal ore contains impurities. If you go for leaching, it is 100% pure. So now after that we go for roasting or we go for calcination. In the process of roasting and calcination, whatever the impurities present in the metal ore does not go. We only remove the water or we oxidize, we remove this wet, we convert wet ore into dry ore. And if it is a carbonate ore, carbonate ores are decomposed into oxides. When you go for roasting, in this process also only the sulfide ores are being oxidized and the wet ore become dry. So the remaining impurity remain with the metal ore. When you reduce them, ores are being reduced. But what will happen to the impurity which is present in the ore? And if this impurity is present in the ore, that makes the metal very impure and not suitable for our use. That will make the metal soft also. So it will not be able to bear this so much of strain that you are going to put on the metal. So how to purify ore? So purify ore in the process of its reduction. So in the process of reduction, when you purify the minimum amount of impurity which is present there, so we use a chemical substance, and that substance is called flux. So what is flux? It is a chemical substance which is added, in the process of smelting or reduction of ore to remove the impurities present in ore. Right. आराम करो So flux reacts with the impurities. What do you call it? Impurities has a name, na? Or gas to form an infusible mass. Generality from generality. This is like English should be, my English should be good and perfect. Which is lighter and insoluble in molten metal. I will not write here. And lighter, insoluble in molten metal, and floats, known as spelling of gangrene. This to form insoluble known as slag. Okay. All. Now, classification of flux. See, flux, I told you that it's a totally a chemical process. So in that case, if the, whatever the impurity that you have there, you must know their chemical nature, whether they are acidic in character or basic in character. So you will use the opposite one. So you call it acidic flux, and second one is called basic flux. Something is wrong with the ink. Huh? It doesn't want to go. So what is acidic flux? These are chemical substances which react with basic impurities present in ores, such as calcium oxide, magnesium oxide, iron oxide, etc. Example, silicon dioxide, sand. Silicon dioxide is acidic. Okay. Then borax, Na4B4SO7. You have seen this borax is being profusely used by the jewelers. Okay, they are used in jewelry. They remove the impurities present in gold. Okay, and see, when you remove the impurities, gold shines. Because of that, borax in Hindi, it is called suhaga. Because of that, that is a saying in Hindi is called sone par suhaga. Means if you use borax while in the treatment of gold, huh, then you will find the impurities in the gold is being removed and the gold becomes more pure and it shines. Okay. Now here this silicon dioxide that I'll show you one example. Ferrous oxide is present in roasted copper ore and is removed by silicon dioxide. So what happens in the copper, that copper extraction I'll do it. So here we use sand, and if you heat it, you get now here iron silicate. So what is this? This is flux, this is gangue, and this is what? This is slag. So this ferrous silicate will float on molten copper. So with the help of big say spoon, huh, you can scoop it out and throw. Right.
Done, sir.
Okay. Now we'll go for basic. Okay. For chemical substances used for the removal of basic impurities. Oh, sorry. Acidic impurities are called like acidic impurities like what? Like sand, silicon dioxide, or phosphorus pentoxide, P4O10, are called basic flux. Okay. So, example, what are the basic flux we use? Calcium carbonate, magnesium carbonate, etc. When we will discuss about the blast furnace, you'll find we are using this type of substances. See now what happens now. When you heat, first of all, calcium carbonate, because we are in blast furnace, we heat it, so we know the carbonate will decompose to give you what? Calcium oxide and carbon dioxide. Now this calcium oxide will react with sand. So this is flux. This is gain. And you'll get here calcium silicate. This is slag. So now we'll go for purification of. So as far as possible, we try to purify everything in the furnace. After that also you'll find metal still contains impurities. Why? Because metal that you obtain is solid, is so compact, impurity will remain inside. It is difficult for us to remove. So you have to go for purification of metals. So never see in my note that I have sent you, I have written many other processes, but only in your book, only few processes are given. Okay. So first process is distillation. Well, this is not being done. Okay, can you hear me? Hello?
Yes, sir.
Oh. Distillation So in this case, you know that impure metal is being taken in a container and we heat it. The vapors will come out and that vapors will be cooled and you will get pure metal. But these are being done only for those metals whose melting point is very less, like mercury. Mercury is a liquid, and second one is zinc. So generally, for other metals, you do not go because if the temperature is very high, so it is not cost effective. Sometimes you can go for lead also. All right. So this is the first process. Second is called liquefaction. So not liquefaction, liquation. Sorry. This is called liquation. This is also done only for one or two metals. Liquefaction is done for those metals where you find the melting point of the metal is less than the melting point of their impurities. So it is being heated in a special type of heat. Okay. So here the impure metal is being taken and this is like this. And here you heat it. All right. So it is a slope. It is a slope is there. So when you heat it, as I told you, the metal whose melting point is less than impurities, the molten metal will roll down and it will collect here, and the impurities will leave. So in this case, as I told you, this is being used for mercury, zinc, and sometimes lead. Here it is only done for tin because we found the impurity that is tin oxide, melting point of tin oxide is higher than that of tin. So in that case, we go for this type of liquefaction. So these are for specific substances. Okay. Then I'll tell you a little bit about thing which is not in your syllabus. It's called polling. Polling word has come from pole. So what is called pole? Pole are nothing but the tender branches of the tree. Or you can take bamboo also. But that is also not dry bamboo. We take green bamboo. So this we know whether it's a bamboo or a tree, the branch is made up of what? Made up of cellulose. Cellulose is an organic substance. Okay. So what you do to the molten metal, we stir it. Just like suppose you have seen no one in a big party and all these things, the rice is being cooked in big utensils, and continuously you will find with the help of some wooden or maybe steel one, they keep on moving this one. So same way the ore is being melted and is being continuously stirred by the uh, poles. The poles can be made of from bamboo also, or it can be made from the tender branches of tree also. So now in the hot one, when you put, the cellulose get converted into what? Cellulose got totally got burnt and converted into carbon, pure carbon. Okay, and this carbon reduces the oxides of the metal. They reduce the oxides of the metal, and metal are being set free from their oxides, and rest of the substance oxygen goes out in the form of carbon dioxide or carbon monoxide. So that way you can get pure metals. Okay, this is not that cost effective. All right, this is also being done, and in many metals are being purified this method. One of them is copper. Copper is also being purified by the process of polling. Then third is called cupellation. Cupellation is generally done for the purification of silver because silver contains the impurities of lead. So this is being in big type of spoon only they are being heated it, and when you heat it strongly, you'll find it comes in contact with the oxygen, and you'll find a white type of fire comes out from there. So in that case, what happens? The oxides of the lead get oxidized and evaporate, and rest of the substance that you get it on the spoon, that is nothing but pure silver. So anyway, these two things are not in your syllabus. All right. Now we'll go for 5. This is being done in large scale. We call it electrolysis. refining. So this one, you know, this is an application of electrolysis. Whenever you want metal of high purity, in this case, we go for electro refining. That we use it for silver, uh, copper, gold, then aluminium, then chromium, nickel. We use it in large scale where you want more than 99% pure. So what you do there in that case? See, in this case, big tanks are made. So I'm only showing you say the front portion. All right. So let me take the example of copper. Hmm, Copper. So whatever the copper, that impure copper that you get, we call it blister of copper. Okay. And then when I go to extraction of copper, I'll again explain to you. So we have taken copper, and the big that molten copper do you get, then we solidify into some specific shapes, then we make them as slabs. All right. So now you know on the right hand side you have to put cathode, and the left hand side you have to put anode. Okay. So in that case, what we will do? So this is the negative electrode, negative, and this is the positive. So this, in this case, what you do, we take these big slabs of copper. These big slabs of copper. Okay. This is the one, and we tie it with the hook. And here you take a very thin sheet of copper. Okay. So what we will write now here? Impure copper slab. And what is this? This is anode. And this is what? This is cathode. So what we will write here? Thin sheet of pure copper. And what we will put here? We'll put here electrolyte you have to put. So we'll take here copper sulfate. And now this is being connected to an emitter. You can see how much amount of electricity is going. That this is that Faraday's first law, remember. So what is going to happen? You are supposed to write here now cathode and I told you dear that there are two types of electrodes are there. One is collective electrode and passive electrode. Passive electrode only conduct electricity, it does not do anything. And active electrodes takes part in the chemical reaction. So here copper, passive electrode is platinum, and active electrodes, rest of the metals are active electrodes. Okay. So now what is going to happen here? You see. So I'm supposed to write cathode and followed by anode, but I'll write this reaction first. See here, anode, what you have? Impure copper. So in this impure copper, what will have? We have taken copper, and in this case, what will happen? The copper is going to lose electron. It will go into solution along with the release of 2 electrons. So from here, only the copper will adjust the voltage. Voltage will be adjusted here with the, and because we know about the standard reduction potential, so we'll adjust the voltage in there only. So from here, only the copper ion will lose electron and go to solution. Other metals will not, because you have supplied specific voltage for that one. And this electron will come here. What in copper sulfate you have copper ion. Copper ion is there. So let me write here now. Copper sulfate aqueous. It will give you Cu2 plus aqueous plus sulfate aqueous. So this copper ion from the solution will go to the cathode and it will collect these 2 electrons and it will be converted into solid copper. So what we will find gradually, all this slab will go into solution, and then gradually you will find this thin copper, that sheet, it has become thicker and thicker. So all the pure copper has been deposited. Now, impurities which are present there, what will happen? They will fall down and they will collect here at the bottom. Okay? It looks very dirty. Because of that, we call it anode mud. We call it anode mud, or we call it anode sludge. So everything will fall down here and you will get 99% copper. So this is I have shown you from the front side. So in that case, you'll find in a big tank, maybe 50, 60 such things will be there. So you can repeatedly convert or purify copper. And this one is a silent process. You only have to start it. And when you try to come and see, check whether the slabs are there or not. When you find the slab has exhausted, everything is fallen down. So switch off the current, put new slab here, and it will run continuously for 24 hours. Now see here. What we'll do with this dirty substance at the bottom? Actually, we are supposed to throw it because we call it anode mud. Why you call it? Because all the dirty substances or unwanted substances which falls down and looks like a mud, because of that, we call it anode. But this one you do not throw it. You know why? Because impurities present in copper they are also equally costly. So they are, remind it, these are all metals. So this can be zinc. It may contain zinc. It may contain silver. It may contain gold, and it may contain platinum. Because of that, this anode mud is not thrown. Please remember, anode mud, it is a short note, sometimes comes for 1 mark. So do not ignore. So high purity substances are being used. We require copper, extremely pure quality of copper is used, because in that case, because the copper is being used in our making different electrical and electronic items. So if any impurity is there, it will lead to resistance. The flow of the electricity will be resisted, and it will lead to heating up of that junction, and you will find your instrument will get spoiled. Okay, write down. Okay, then let me write down what is anode mark. Suppose it comes, then you will say, sir only told you did not write anything. There is a problem with the sir. Huh? Everywhere teacher is being blamed. So what you will write now here? Anode mark. While purifying metals by electrolytic method, the impurities get precipitated below anode and is called anode mark. This also contain, this also may contain, because all may not have, no? This also may contain some important and costly metals.
Done, sir.
Okay, that means that okay. Now we'll go for a very important method of purification, and also is important for exam. I feel like destroying this board. That this ink has become too concentrated. I don't know. Sometimes two good things are also not good. Let me see. You know how I'm cleaning? I'm cleaning with hand sanitizers because they contains alcohol now, so alcohol removes the stain. Yep. Okay. So this one we call it zone refining. Zone. This is very, very important. Zone refining is done for those metals which should be almost 100% pure. Generally, this type of purity only we want only when we want to use them as semiconductors. Okay, so let me write it. This method is used for metals which are required in very high purity. Example, extremely pure silicon, germanium, boron, indium, and gallium. To be used as semiconductor. These examples are asked. Okay, these examples are asked. Okay, it based on a principle. This method is based on the principle that impurities are more soluble in melt. Try to understand melt. Melt is what? I'm not, I'll remove that inverter. Melt is what? Where the metal has become soft. Then in the solid state. So how it is being done? Okay. So first I'll draw it, then I try to show it. Say, this is, we take a metal, we convert metal into rods. Right. Okay. And then we melt it with the help of a circular burner. Have you seen any circular burner? Hey, all of you don't remain quiet. Anyone have seen any circular burner? Huh?
No, sir.
None of
No,
you have, huh? None of you have seen. Who told me no just now? Who? Grace or what? Or Gitanjali? Huh? Tell the name.
yes, sir, that's me.
But tell me the name. I can't see you, na?
Grace.
Grace. Grace, how in your kitchen, that gas stove you have, what type of burner you have? Is it square or triangular?
Circle in shape.
Huh?
Circular.
Then why do you say that you have not seen? See, Grace, very nice. In our kitchen, we have this type of burner. Lot of holes are there, na? But thing is that hole is from the top, so the fire goes to the top. in circular burner, what will happen? If this is this circular burner, in our gas stove, holes are on the top. Here the holes will be in the middle. When the holes are in the middle, the fire will occur in the circle or not? Huh? So in that case, what happens? We take a circular burner. Say this is the circular burner you are having it. Okay. So circular burner. Please excuse me for such a bad drawing. What will happen now? The fire will be in this direction or not? The fire will be in this direction. So now, when you heat it in this place, then the metal will become soft. Huh? When this metal will become soft, because we'll have a handle. So with the help of handle, we'll gradually move this burner, gradually move this burner to this. So as you move this burner to this side, then what will happen? As you move it, then this place the metal will become again solidify, and the softness will move from, as the burner moves from right to left, or you can put in the left also, no problem. Yeah, I'm putting here in right. Right to left, you'll find the softness will approach to this side. So ultimately, say the burner has come here. Ultimately, the burner has reached here. Okay, burner has reached. So what will become? You will find this place becomes soft. Okay, and this from here to here, it has now again solidified and it has become hard. You know what will happen? All the impurities will rush towards this soft portion. All impurity will rush towards the soft portion, and this will be 100% pure. So we'll switch it off, allow it to cool down. When we cool this one, what we'll get? We again get the same rod. So here we'll mark it now. This portion will cut and throw, and this portion will be 100%. So this is the technique of zone refining. Okay. So now we'll go for another method. This is called vapor phase effect. But that is also not being used so much frequently. But for examination point of view, it is very, very, very important. So in vapor phase refining, again a principle is there. So first I'll tell, then I'll. As I told you, these are not being used frequently. These are used for some specific metals. The first principle is that the metal should, by reacting with certain chemical compound, should form volatile compounds. Volatile compound means what? They will be converted, compounds will be converted to gaseous state. Second, this volatile compound, if you heat it further, they will decompose to give you the pure metal. Okay. So what is the principle? This principle is being asked. Huh? Okay. Especially I have found in MO sometimes they ask. It is based on the principle that the metal should form a volatile compound with an available reagent. And second, the volatile compound should be easily decomposable so that pure metal can be obtained. So now I'll show you example. Example I'm going to show you. Okay. So first one I'll show you one process. This is very, very important. One we call it mons process. So this is being used for only purification of nickel. In this process, nickel is heated in a stream of carbon monoxide. To form volatile, we call it nickel tetracarbonate. The nickel tetracarbonyl, when heated at higher temperature, decomposes to give pure nickel. So let me write down. So nickel plus 4, this is gas. When you heat it at, excuse me. Oh, না মই ক্লাছ লৈছো একো নহয় মই আজি মই ভাইস প্ৰিন্সিপালৰ লগত মই কথা হৈ বস্তুখিনি পঠিয়াইছো ৰাতিপুৱা মোৰ ক্লাছ আছিল দুপৰীয়া পঠালো কালিহে গম পাম তেওঁৰ লগত মোৰ নাই দিয়া মই এই ক্লাছ চেক কৰি পঠাম আপোনাৰ মেছেজ কৰি পঠাম আৰু আচ্ছা বোৰ্ড তাত কি হোৱাটছএপ আছে নেকি বোৰ্ড মোৰ ওচৰত আছে বুলিহে তেওঁৰ লগত মই মানে কথা পাতিছো আৰু আপোনাৰ নাই হ'ব মই পঠিয়াই দিম ঠিক হ'ব এতিয়া নহয় মই বুক ক'লে বৌয়ে বুক পঠিয়াই দিব মই পঠাম আপোনাক ক্লাছ শেষ কৰি পঠিয়াই দিম কালি পাহৰিলো So you'll get at 330 to 350 Kelvin, you'll get nickel tetracarbonate. Okay. In your book, the square bracket may not be given, but when you study coordination chemistry, you will automatically put this one because it is a complex compound. Now, when this nickel tetracarbonate is further heated at higher temperature, 450 to 470 Kelvin, it will break down. It will decompose to give you nickel plus carbon monoxide gas. So this gas again can be used for purification of the rest amount of the nickel. So this is again important for your exam.
sir.
Okay. Now we'll go for another method. Physical phonarcal method. ARKEL. Here, this is not being pronounced as
Vo. We call vo.
physical phonarcal method. In this process, metal is converted to volatile, unstable iodide. Which is further heated to decompose to give pure metal. This is being used for the purification of titanium. It's a very important metal, and zirconium. Titanium and zirconium. Okay, now we'll do. So we have taken titanium solid. This will be reacted with iodine at 523 Kelvin. So you will get now titanium I4 tetraiodide. Okay, now this is being heated in 1700 Kelvin.
This is not being heated by fire. We electrically heat it. Such a high temperature generally always created by electric.
So again you get here titanium and 2I. Then zirconium. So I'll write here now impure. Impure. 2I2. 870 Kelvin. You get here now zirconium tetraiodide. This is being heated at 2075 Kelvin to get again. This is pure. You just also get pure and 2.
So this is the method. The last one which I am going to discuss now is called chromatography. See, this is a very special technique of purification of metals. And it based upon the concept of adsorption. It is based upon the conception of adsorption. What type of metals will purify this one? This method is being used for purification of mixed metals, which is being mixed with some other metals, but they almost show similar properties. So other technique cannot be used. Chemical and other physical methods cannot be used. You have to use this one. See, different metals have different molecular mass and different intermolecular forces of attraction. So in this method, when you take this mixture or impure metal, we put it into a column. Okay, it is a glass column and is being packed with adsorbent. Okay, this is stopper is there. No stopper, a plug is there. Is packed with adsorbent. And the impure metal. Impure metal means it contains other metal. But those metals almost show the similar chemical and physical property as that of the metal. So if you use any other chemical process, you will find both of them will come together. So in that case, what we'll do? We put that mixture here. Okay, impure metal is being used. So in that case, what you do? But as because I told you that different metals have different intermolecular forces of attraction because it depends upon their effective nuclear charge, and an effective nuclear charge, all of them will not be same because they have different number of protons and different number of electrons. So when you put it, so the metals get adsorbed with different forces of attractions. So after that, what you do? We use some solvent. Now metals or impurities which are loosely bound, it will flow with the solvent. And my metal will remain on the top. Or it may happen another way also. My metal is having weak forces of attractions and others are having strong forces of attraction. So the metal which I want to pure, it will flow down. Others will remain. All right. So along with the liquid, that metal will flow. All right. And we'll collect it. We'll distill the liquid. So solvent will distill it and pure metal will get it. So generally we use it for those metals which have very close proximity in the properties of the impurities. And generally, what type of metals are being separated by this chromatography technique? So the actinoids, sorry, lanthanoids. There are 14 elements are there. Lanthanoids and actinoids are purified or separated by this technique. So many things I try to tell you everything, but if some of the words are missing, you can get it from them. Thank you.
Thank you, sir.
Welcome.